Lecture 18, Redox Reactions, Part 2. So this is the second part of identifying these redox reactions. So in this case, now that we've seen that these redox reactions involve changing of oxidation numbers, we're going to use that then to talk about balancing these redox reactions, which is in some way similar to balancing chemical reactions we've talked about in the past, but it's more involved because now we can actually change what's there based on the charge. So now we're not only going to balance mass by the number of atoms that are there, but we're also going to have to make sure we balance the charge. So again, there is over 6 steps to balancing these chemical reactions. So let's look at the oxidation of iron 2 plus to iron 3 plus by this dichromate ion in an acidic solution. Okay? So the first thing we have to do is write an unbalanced equation for reactions in their ionic form. So we're going to look at these. So we know we're going to take the Fe2 plus and react it with the dichromate Cr2O7 2 minus to give us Fe3 plus and the chromium ion Cr3 plus. Right? So from here, we are then going to break those into their two half reactions. We're going to decide which is the oxidation. In this case, it's the iron. Iron is going to go from a 2 plus to a 3 plus, which means it's losing electrons, right? Loss of electrons is oxidation, while the chromium going from a plus 6 to a plus 3 is being reduced. It's losing or gaining electrons, excuse me. So Leo goes gain of electrons is reduction. So now that we have these two half reactions, we're going to balance those individually. Right? So the first thing we're going to do is balance those atoms other than hydrogen or oxygen. Right? So if we look at the oxidation reduction or oxidation half reaction, we have 1 iron and 1 iron. But if we look at the second one, the reduction, where we have this chromium, we start with 2 in the reactant side and we go to 1. So we have to take care of that first by changing the fact that now we have 2 chromium as the products. Right? So now those other elements should be balanced at this point. Right? We're still treating them as the two half reactions. The next step is that for reactions, it says acid here, but I suggest in all reactions, you add water to balance out the oxygen atoms, and then H plus to balance out the hydrogen atoms. So again, the oxidation is completely balanced already. There's no oxygen or hydrogen in there, so we're going to ignore it for now. But we do have this chromium. In one side we have oxygen, in the other we don't. So we have 7 oxygens as reactants, which means we have to add 7 waters to the product. Right? Now our hydrogens aren't balanced. We have 14 hydrogens on this side, so we have to add 14 H pluses over there. Right? So now we are sort of mass balanced. We have all the mass we need, or all the atoms are accounted for in the number we need. The next thing we have to do is the charge balance. We have to make sure that those numbers of electrons that are transferred in that half reaction are shown. So in this first one, the oxidation, we go from a 2 plus to a 3 plus, which means we've transferred 1 electron, we've lost 1. So to get the total charges to be the same on both sides, we have to add an electron to the product side, that negative charge. If we look at the bottom, this reduction, without the electrons, we have 14 pluses, 2 minuses, so a total of 12 plus on this side. On this side, we have a total charge of plus 6. So the difference between the plus 12 and the plus 6 is 6. So we have to reduce this side by 6 electrons. Right? Or we can look at the oxidation, the change in oxidation numbers. We went from a plus 6 to a plus 3. But there was 2 of them, so that's a change of 3 electrons. So the chromium had to gain 3 electrons. But there are 2 chromiums involved, so we have to gain a total of 6 electrons. Either we look at the total charge or just the change in oxidation number. Either one should give us the correct number of electrons that are being transferred. Since these two are transferring electrons between each other, the total number of electrons that are transferred have to be the same. right? So then we have to multiply those reactions so that the total number of electrons that are transferred are the same. So up here we have a +1 or 1 electron transferred here and 6 electrons transferred over there. So we have to transfer a total of 6 electrons. So we're going to multiply this top reaction, the oxidation, by 6 to get those number of electrons to be the same. Okay. So first we're going to balance those things that aren't hydrogen and oxygen. Then we're going to balance oxygen with water, and then hydrogen with H+. Once that's done, balance the electrons, make sure the number of electrons that we transfer are the same, and then at this point we can now add those two half reactions together so that we get the number of electrons that are lost on one side have to be the number of electrons we gain on the other, so those electrons will cancel out. Sometimes there'll be other things that will cancel out. In this case, there's not. So everything else falls down, sort of like Plinko chips if you like The Price is Right, which you should. Right? So everything else falls down, and that gives us a balanced chemical reaction. Right? And you should, again, like every time you balance a chemical reaction, you should go back at the end and make sure that they balance both the atoms and the charge. And here I'm showing the charge balance, so we have 14 positives minus 2 negatives plus 6 2 pluses, so that total is 24, positive 24. If we look on the product side, we have 6 3 pluses plus 2 3 pluses, which is equal to 24. So we are charge balanced and mass balanced. You can do that mass balance on yourself to figure out the number of species are correct on both sides. Right? So in an acidic solution where it's okay for us to have H pluses, this reaction is balanced. But in a basic solution, we don't actually have the ability to have H pluses. So we have to take care of that by adding OH minuses to both sides in an amount that's equal to the number of H pluses. So if we were going to do this reaction, we would have to add 14 OH minuses to both sides. When you take an H plus and an OH minus, react them together, as we've seen in the acid-base reaction, you get water. So on this side, we would have then 14 new waters, and we would have to then correct that since we now have water on both sides. We'll do some of these examples in class, so we're not going to go through them here, but just remember that this is the steps we're going to take. Write an unbalanced reaction, separate into their half reactions, balance the number of species that aren't oxygen or hydrogen, then balance oxygens with water, hydrogens with H+, make sure that the number of electrons, then balance the charge by adding electrons to one side or the other, make sure that the number of electrons that we have transferred are the same, add those two together, and then determine what type of reaction we are in. If it's acidic, then you're done. If it's basic, then you have to add the number of OHs for the number of H pluses, and then go back and correct for water. Okay? It's a fairly involved process. Again, we'll do several of these in class. So now we should be able to recognize and balance these redox reactions. So let's take a couple minutes and just sort of talk about the different types of these redox reactions. There's 4 we're going to talk about. I really want you to be able to recognize redox reactions, not necessarily classify them as we have here. But the first one, the type of redox reaction we're going to talk about, is a combination, where we take 2 or more substances and combine them into a single product. Decomposition is the opposite. You're taking a single compound and breaking it apart into 2 or more. Right? The most common type of redox reaction, at least the one you'll be most familiar with, are combustion reactions. So anytime we do a combustion reaction, where we take some species and it reacts with water, or excuse me, not water, oxygen. So the species reacts with oxygen to form carbon dioxide and water. That is a combustion reaction. Right? There could be other products if we have things that aren't only carbon or hydrogen, but anytime you see something reacting with oxygen, or you use the term combustion, that is a redox reaction. And the last type, there's 3 subtypes of that, is a displacement reaction, where we're taking one element and sort of displacing another one of similar type. So this first type is hydrogen displacement. We're taking some metal and we're displacing hydrogen with that metal in the reactant, in the compound. So the second one is a metal displacement. We're taking a metal and replacing it with another metal displacement. And the last type is this halogen displacement. We're taking a halogen, that group 7A, and we're replacing it with a different one. Right? Again, I don't necessarily think you have to be able to classify these different types of reactions or subclassify them, but you should be able to recognize the main of them as what they are, those main types: precipitation, acid-base, or redox. So let's look at this example here. We can classify these based on their type, just sort of a general thing. The first one, we go from two things that are aqueous to a solid. We recognize that as precipitation. The next one, we have ammonia plus a H+. So the oxidation numbers aren't changing. We should recognize H+ as an acid. So this is an acid-base reaction. Ammonia is actually a base, so if you memorize that, that's an acid-base reaction. The last two, we look, zinc is going from an oxidation number of 0 to a 2+. Hydrogen is going from a +1 to a 0. We're changing oxidation numbers. That is a redox reaction. The last one, again, changing oxidation numbers. We see that as a redox reaction. So now at this point you should be able to not only recognize these types, but balance just about any chemical equation.
Dad, I done did it.